So, hi, good afternoon, everyone. So, how do I change the slides? So from here, okay, okay, good, okay, okay. So, yeah, I think the way this workshop is planned between Professor Shoiko Chatterjee and myself. Okay, so I think we are going to have four. Okay. 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 So we are going to have four sort of lectures, come hands-on demo kind of things. Okay. We will try to cover the. Okay, I think. Yeah, we'll try to cover the. The a reasonable portion of machine learning. Okay, so today's lecture is going to be on foundations of data science. Okay, so okay, so let me start with the overview. I think all of you know what we are talking about, but just to be clear, so you have seen this Face ID, Apple Face ID, right? Or Microsoft also has its this thing. So how does it work? So there's a component underlying which is called a face recognition software, right? So it's a software that recognizes faces. Okay. Now, how do you think that software, that piece of software was written, right? So in order to understand that, you have to you have to appreciate the fact that it's so to us humans, it looks like a very trivial thing that we can recognize people by their faces. Okay, so in fact, just before, so I met some of you, and I could immediately recognize your faces, even though I did not remember your names. Okay, so I had met you earlier, so I could recognize your faces, but I could not remember the name. Okay, so face recognition is a very fundamental thing that we humans do. Okay, and the way we we do not use any kind of logic. Okay, so for those of you who have written programs, you know that you have to use some kind of logic. Okay, so a particular parameter is greater than a particular value, or sum of two things is this thing, but we don't use any logic. Okay, so how do we how do we recognize faces? Okay, so the way we recognize faces is that we learn to recognize faces. Okay, so what happens is, right, when we are a small kid, recognizing faces, okay, is something that helps us in sort of our survival tasks. And so we sort of naturally, right from the time when we are kids, okay, we learn to recognize faces. Okay, so and so basically that is the key idea. Okay, that so what is the idea behind machine learning? So the idea behind machine learning is that you don't write a program, or you don't write logic. Okay, what you do is you sort of have a program or a machine, okay, which takes in a lot of data. So remember how the child works. The child looks at a lot of faces. Okay, so he or she meets a lot of people, looks at a lot of faces. Okay, and then they sort of for some reason they they find it useful to be able to recognize faces. Okay. So there are two things. One is that the child sees a lot of faces. It's important. If you keep a child in an environment where they don't see any human faces, they will never be able to learn how to recognize faces. So this is number one. Okay. Number two is there should be kind of an objective function. Okay. So there should be a reason for this machine, or this, in this case, the machine is the child. Okay. To be able to recognize faces. So for example, maybe they want to first learn to recognize their mother's face. Okay. Then maybe they want to recognize their father's face, their, other maybe close relatives' face who keep on, visiting them more frequently, and so on and so forth. Okay. And they do that because they know whom to ask for food, or they know whom to ask for, whatever problem when they are in a problem. So that is the objective function. Okay. So so that is the thing. Okay. Okay. So examples, okay, in our parlance, or in the machine learning parlance. Okay. And the objective function that you will be optimizing will be called either a loss function or an objective function, depending on whether you want to maximize it or you want to minimize it. Okay. So these are the two main things. Okay. Okay. So what does the program have to do? Okay. So in case of recognizing faces, what does the program have to do? So the program has to assign a label to that face that it is seeing. Okay. So this is called a so what type of machine learning problem is this? Classification problem. Okay. So classification problem is something that we will look at. Another kind of thing, you may be asked to do is a machine may be asked to do is predict a continuous value. Okay. So this kind of problem is called a regression problem. So today we will be discussing mostly these two problems. Okay. Now these two problems, so this is one part of the puzzle. Okay. Another part of, so please feel free to stop me if I'm not getting through at any point in time. I'm just going a little bit fast because I think most of you know this. Okay. Okay. So now you see and regression together, they are called supervised learning problem. Okay. So what is what is the so you must have heard about these terms supervised learning and unsupervised learning. Okay. So and then in between there are semi-supervised learning tasks also. Okay. So what are these? So why am I calling these tasks as supervised learning tasks? Okay. So the reason is that in case of supervised learning task, the thing that you are predicting, okay, in statistics literature, it's working. Okay, thanks. Yeah, this is a lifesaver. Okay. Okay. Yeah. So in supervised learning tasks, okay, the thing that we are predicting, okay. So in case of classification problems, it is the class label. Okay. In case of regression problems, it is the value that I am predicting. Okay. These are part of the input data, or these are given in the examples. Okay. So these are part of the input data. Okay. In case of unsupervised learning problem, so let me see if I have it. Yeah. Okay. Yeah. So a machine learning algorithm takes these examples and produces a program that does the job. Okay. So we have discussed it in greater details. Okay. We'll come to the new cases part. Okay. So here is an example of a classification problem. So essentially the problem here is that you are given some handwritten digits. Okay. and you have to classify them between 0 to 9. Okay, and you can see that it's not very easy to see which one of them is 2. So this is probably, I don't know, is this 2 or a 3? Even I can't recognize. Okay, but these are some of the things. Probably, you can teach a machine to actually learn to classify them. Okay. Okay, yeah, so these are some examples. We have seen facial identities or facial expressions, okay, handwritten or spoken words, okay, so yeah, medical images, okay. So these are so these are some of the supervised learning tasks, okay. So then prediction of, for example, future stock prices or currency exchange rates, okay. These are what kind of tasks? So these will be regression tasks because you are predicting a continuous number. So you are trying to predict the stock price or you are trying to predict the currency exchange rate, okay. So these will be regression. In fact, there is a component, so I think some of it will also be discussed towards the end, is there's something called time series prediction, okay. And a lot of the models are what are called auto-regressive models. So sometimes what happens is you are given a time series, okay, and you have to predict a future value based on a series of the past value, okay. So that's the time series prediction problem, okay. But underlying that is again a regression problem, okay. So yeah, so these two are very fundamental problems. Classification and regressions are very fundamental machine learning, okay. Okay, so now, yeah, so there are other tasks like, for example, generating images. Okay, now these are uh, Yeah. Should I just put it here? Yeah. And then how can you transfer it to there? Upload it to Google Drive or something? Yeah.
We can reshare it and
Yeah, this is fine. Okay, good. Good. Yeah, perfect. So, yeah, okay. So, yeah, so we are sorry for the interruption. So, yeah, so as we were discussing, so we were talking about the linear basis function models. Okay, so so phi j is the jth basis function. Okay, and we are using a linear model, a model which is linear in the basis function phi j. So we our model can be written as W transpose phi of x. Okay. Okay. So what are the different types of basis functions that you can use? Okay. So we already saw polynomial basis function where phi j of x is x to the power j. Okay. Now what you can know, I mean, probably many of you know this. Okay, that you try to select a set of basis function which spans a large space of functions. Okay, so for example, this polynomial basis function, okay, it can so it can pretty much so it spans the entire space of what is called L2 functions. Okay, so Lipschitz continuous functions. Okay, so this is a sort of a good basis function. Okay, you can say. Okay, another kind of basis functions which is very commonly used are these Gaussian basis functions. Okay, so what are they? So these are basically so this one does not have any parameters except the power. The Gaussian basis function has these parameters mu j and s. Okay, so mu j is called the location parameter of the Gaussian basis function. Okay, so basically what this phi j is measuring is proximity of x to mu j. Okay, okay, so it's a graded proximity of x to mu j. So sort of x minus mu j, you can see that it exponentially decreases as x moves away from mu j in either direction, either positive direction or negative direction. Okay, and how fast it decays is sort of captured by this parameter s, which is also called the bandwidth parameter. Okay, so the larger s, okay, or it's also, yeah, sometimes called the scale parameter. Okay, so if s is very large, okay, then it decays very fast, basically. Okay, okay, so now so this is kind of measuring the proximity. Okay, there are class of basis functions called the sigmoidal basis functions. Okay, so they measure thresholding. Okay, so they are, okay, so location and bandwidth parameter, or sometimes location and scale parameter. Okay, but in this case, it's what you're measuring is, so the graph of it, so the function is sigmoid. Okay, and the function is mentioned in the slide, as you can see. The graph of it looks something like this, where you have, I don't know, those online can see this dot? Okay, okay, very good. They can't see the dot, right? Okay, let me then try to use this. Yeah. Okay, so yeah, so you can see here that so this is the shape of the function. Okay, and this red function is probably the one with mu j is equal to 0. Okay, you can see that this is basically measuring, so this function is -1 if x is much lower than, so x axis is x and y axis is the output phi j. Okay, so this is much lower, this is this is actually 0, y axis is 0. So if x is much lower than mu j, then the sigmoidal basis function will give an output 0. Otherwise, if it is larger than mu j, it will give a 1. So it's kind of a thresholding function. If x is greater than mu j, it will give an output of 1. Otherwise, it will give an output of 0. Okay. Now, consider so what kind of curves? So let's come back to now our original polynomial basis function thing, right? So what kind of curves can it represent? So it can represent pretty much, so here are some example curves that the linear function with polynomial basis can represent. So, you know, f is equal to x minus x square can represent something like this, x plus x square can represent something like this. Okay, so it can represent a wide variety of curves. Okay, question is, can it represent that sinusoid wave? Okay, so in order to understand, so now what are we talking about here? So here we are manually providing the w parameters. So here that the weight or the coefficient of x is 1 and coefficient of x square is -1. Okay, but here we are so you know, in our introduction we said we don't want to manually provide w, right? So what do we do? Okay, so how do we learn w? Okay, so one of the very popular ways of learning this w, okay, or estimating this w, as statisticians would call it, okay, is to minimize these squared error. Okay, so you have, so what do you need as input? You need data points. What do data points constitute? So data points are xn and tn. Okay, so xn is the are called in machine learning terminology the input features, okay, and Tn are called label, okay. So, and there are capital N many data points. So, basically small n is the running index over the data points, okay. So, for every input feature and the constant parameter that we have of this machine learning model, I can predict I can compute this y of xn comma w, okay. So, this we know, this is the linear basis function model, okay. Now, so this will compute a real number, okay, and I already know from Tn, if I pass xn here to this linear basis function model, what should be the output. So, what do? I take the difference and then I square it, okay. So, this is the squared error, okay, or this is also you can it's called either the squared error or the squared loss, okay. So, this is the squared error, which is the difference between the predicted value and the given ground truth for each and every training data point. So, the squared error is computed and then we sum over it, okay. So, this is the total squared error or squared loss over the entire training data set that is provided to you with capital N many training examples, okay. So, what is the best parameter W? The best parameter W is the one which minimizes this squared error or this squared loss, okay. And this objective is called least square estimation, okay. So, we are doing least square estimation of W, where we are choosing that particular W which minimizes this squared loss. Yeah. Why are we taking a half? No particular reason. So, it's only that the computation becomes, less cluttered, okay. But as you can understand, if I don't put a half here, W star will be exactly same, okay. So, there will be no difference whatsoever. Yeah.
So, sir, I have a question here that while minimizing this EW, do we are we
Yeah.
estimating the
So, if you see here, so there are two things, right? So, we have to compute the basis function, but if, for example, let's go to the polynomial basis function, right? So, we can just compute this basis function given the x, okay. Now, here x is nothing but xn, okay. So, xn is the nth data point which is given as input, okay. So, what is the unknown here? The unknown here is actually w, okay. So, we can compute all the basis function phi of x. So, if you see the whole model, so this is the whole model, right. So, phi of xj we can compute. What we don't know is this w, okay. So, that is what we estimate, okay, using this particular formula, okay. So, sometimes we can also try to determine these hyperparameters, but we will not get into that right now, okay. Okay, I hope that is clear, okay. Okay, now of course the next question is that why is this, why did we get to this whole least squares objective, okay. And there is a theory behind it, okay. And the theory goes something like this, that what we assume, so another way of motivating this least square objective is that we assume that our t, or the true label that we got, is equal to this linear basis function model output, okay, whatever is the predicted output, plus some noise epsilon. So, this noise is random quantity. Up till now, we had not seen any random quantities, okay. Everything was a variable, either a given known variable or a unknown variable, okay. But now, we have added this epsilon, which is a random variable, okay. And the distribution of this random variable is assumed to be a Gaussian distribution, okay, with 0 mean and 1 by beta covariance, which is also sometimes called the so this is called the confidence parameter. Okay, so basically 1 by beta is equal to sigma square, which is the the variance. Okay. Okay. So this epsilon is following Gaussian distribution with 0 mean and 1 by beta variance. So you can see that what we are essentially assuming here. So for those of you who know, I think most of you know that Gaussian distribution usually is highly concentrated around the mean. Okay. So what we are assuming here is basically that this noise that is getting added is highly concentrated about 0, but it can be positive or negative. Okay, so it can be both positive and negative, and depending on beta, it will be somewhat concentrated around 0. So mostly it is 0, but it's not exactly 0. Okay, and it's a random quantity. Okay. If this is the case, then we can develop what is called the the maximum likelihood estimator for this particular model. So what do we do? So now we say that given this probabilistic model, now this becomes a probabilistic model. Okay, so the moment we add this noise, t also becomes a random variable. Okay, and we can write a probability distribution for this random variable, and it so turns out, okay, that this probability distribution has mean yxw. Okay, notice here this yxw is unknown, but it is not random. Okay, so this is a fixed number. Okay, and yeah, so t is also now following Gaussian distribution with mean y and the same variance beta. Okay, and then if we have as previously capital N many observed inputs and the corresponding t's, okay, what we have here is the likelihood function. So what is the likelihood function? Likelihood function is the probability of observing all the inputs given that the inputs are assumed to be independent of each other. Okay, so that is why we are multiplying. So this term here is the probability of observing this Tn given you have seen this, this W and Xn. So you don't know W, you are going to estimate W eventually, but for the purpose of this formula, you assume that you know W. Okay, so then given this particular mean and this variance, what is the probability of observing Tn? Okay. Now, this is for the nth data point. You can do this. You can take a product over all the data points, and that will give you the likelihood. Okay. Now, so what happens here is that we typically don't look at likelihoods because these are very, as you can see, all of these numbers are between 0 to 1, and you are multiplying capital N of them. N sometimes is in hundreds or thousands. So these numbers are not very, these are very small numbers. Okay, and at the time of computation, if you try to compute the likelihood function, it will almost surely lead to a numerical error or a underflow. Okay, so instead what we look at is the log likelihood function. Okay, now why do we, so by the way, before I go there, what is, so what do we, so remember we were trying to estimate this W. Okay, and we ended up defining this probability of the data set, which is we call the likelihood of the data set. Okay, so what is the utility of this likelihood? The utility is that according to maximum likelihood paradigm, what we will say is that the parameter W, the best parameter W for our model, okay, is the one which maximizes this probability of the data set, or which maximizes the likelihood function. Okay, So this is the maximum likelihood estimate that I want to compute. Now, like I mentioned, instead of computing the maximum of the likelihood function, what we compute is actually the maximum of the log likelihood function. So what is the log likelihood function? You basically take the log of the likelihood function, and in most machine learning cases, under this is called the IID assumption, which is the independent and identically distributed data assumption. Okay, under this assumption, the it's a product over probabilities, and that in log domain becomes summation over probabilities. Okay, like this. Okay, and if you just do a bit of computation, what you can see is that basically you will have few terms. So first term depends on beta, second term is kind of constant, this term. Okay, it only depends on the data set size, and as we know, I mean, so this is kind of fixed, so there is nothing doing here. The first term depends on beta, and then there is this minus beta times ed, which we had seen earlier. Okay, so you can just do the algebra here, and you will be able to see that this is equal to this. Okay, yes.
Product of probabilities can make the entire value pretty small in line equation.
Yes, that's what I just mentioned. Yeah, which is why we don't do this product ever. In practicality, in when we do the computation or when we write the program, we never compute this product. Okay, instead, what we compute the log likelihood. Log likelihood is actually log of this product, and as you know, the log of a very small number is going to be a negative number. Okay, but it's not going to underflow. Okay, okay, so that's that. Okay, now that brings us to this particular objective. See, now we want to find the best W. Okay, so what will this do? So this beta is, if you remember, this beta was the inverse variance, right? So 1 by beta is the variance. Okay, so the variance is always a positive number. Okay, so the variance cannot be negative because it's it's, you can see the formula for variance. Okay, hence this beta is actually a positive number. Okay, so then what does this mean? If I want to maximize this, okay, what this means is that I want to minimize this ed with respect to W. Other two terms don't depend on W, and the coefficient beta, which is unknown, actually we can also optimize with respect to beta. Okay, but whatever we do, it will always be positive. Okay, so this minimizing this ed, this whole thing is same, sorry, maximizing this whole thing is same as minimizing this ed term of W. Okay, so we get back the sum square error through the maximum likelihood route also. Okay, okay, so now what do we do? So now we come to we come to this particular formulation. So how do we minimize this with respect to W? So we all know we have to differentiate with respect to W and set it to 0. Okay, so that is the typical way. So that will give us the first order stationary points, right? So, and then you can show that this particular function is actually a convex function. Okay, so it's like a function. So if I may, if I want to, just write it here. Okay, so I can write it here. Okay. Oh, okay, we have to switch. Okay, okay.
You can select the pen.
Huh. Right. Okay, and then here, and then color black. Okay, thanks. Yeah. So it's a function something like this. Okay, not like that. So it's like this. Okay. Okay.
You have selected shapes.
Sorry. Okay, thanks. Yeah. So it's a function like this. This one? Okay. Yeah, that is good. So it's a function like this. Okay. And now, so I can delete this. No. This is the eraser, right? Okay, that is also fine. Yeah. Yeah, it's a function like this. Okay. Okay. Yeah. So basically, what I'm trying to say here is that so here, if you have W, okay, if your x-axis is W, okay, the shape is going to look something like this. In other words, if you take two W points, okay, W1 and W2, okay, okay, and you take any W which is a linear interpolation of W1 and W2, okay. So it's like alpha times W1 plus oh sorry, I don't know how to yeah, just this one, yeah, okay, 1 minus alpha times W2, okay, okay. So suppose this is such a point, okay, so W is this, let's say, okay, then so ED of W, okay, is going to be always less than or equal to ED, something like alpha times ED of W1, okay, plus 1 minus alpha times ED of W2. Okay, so so what this means is basically that when you do a linear interpolation between any 2 points, okay, the linear interpolation always always overestimates, okay, the function values compared to the function value at that particular point. Okay, so that function is a convex function. Okay, we can switch. Okay, thanks. And okay, okay, yeah, okay, okay. So anyway, so okay. So this is what we are doing here. So so if so convexity is because we can safely assume that for a convex function, a first order stationary point is also a local minima. It's actually a global minima. Okay. So so hence we can simply differentiate with respect to W and set it to 0. So that's what we are doing here. We are just differentiating ED with respect to W and setting it to 0. Okay. So that's why, if you remember, we had a half here. So that half is now gone, because if you differentiate, this becomes 2 times this. Okay. And then times phi of xn. Okay. So you get a system of linear equations something like this. Okay. Okay. And if you do a bit of matrix arithmetic, you will see that you can solve this using what is called this Moore-Penrose pseudo inverse, which is that you form this Phi matrix, which is this. So your basically your Phi matrix is your rows are feature vectors. So in this case, your basis function vectors. Okay, so phi 0 x1, phi 1 x1 till phi m minus 1 x1. So you are taking a m minus 1 dimensional feature. Okay, and then you have capital N many such data points. So you have n many rows and capital M many columns. Okay, so this is the Phi matrix. This is how you form the Phi matrix, and then you have to compute the Phi transpose Phi matrix, inverse of that, and then Phi transpose T is going to be the solution of this. It's fairly easy to see. You just have to do a bit of a calculation here. Okay. Any questions or comments till now? Okay. So this is also sometimes called okay. Yeah. So these are also sometimes called the normal equations. Okay. And this is a good thing about least square regression, that you get a closed form solution, but there is a caveat here. The caveat is that your Phi transpose Phi has to be invertible. Okay, if Phi transpose Phi is not invertible, then you cannot use this. Okay, this particular formula to calculate, but your WML will still exist. So your maximum likelihood estimate of W will always exist, but you may or may not be able to use this particular formula to calculate. Okay. Okay. Now here is another kind of, you can say, interpretation of the whole normal equations. So what it says is that in case of least square regression, okay, okay, so in case of least square regression, your predicted value, okay, so you see this, okay, so you have calculated this maximum likelihood W, which is the optimal W, okay, and now your Y is going to be phi times WML, okay. So your Y here is the vector of labels, or vector of predicted labels on the training set. Okay. So what is your vector of the predicted labels on training set going to be? So it is going to be phi times WML. You can see this because of your original model itself. Okay. So your W transpose phi of X is basically the Y. Okay. So you can use it to you can use the same formula. Now this WML itself, if you go back here, is again phi transpose phi inverse phi transpose T. So this one actually becomes Y is equal to phi times or this one is actually phi transpose. Okay, so phi transpose times phi transpose phi inverse phi transpose T. Okay, so this matrix is also sometimes called the hat matrix. Okay, so what this matrix is doing is it is projecting your T vector. T vector is the vector of all true labels, okay, onto the space of these features phi 1, phi 2, etc. Okay, so it is projecting this T vector onto the space of phi vector. Okay, so obviously if your space of phi vector contains this T vector, then what will happen to this Y? If your space of all these phi, so this phi vector is clear, I think, to everyone. Okay, so if your space spanned by these phi vectors contains this T vector, then your Y is going to be equal to T vector because there is no projection. It is already in that space. So the projection is going to be the same thing. Okay, that means that so try to understand this. If this T vector is contained in the space of the features, okay, of the training data matrix, then the training set error will be 0 because your y will be t, okay. So there will be no difference between t and y, so your training set error will be 0. Otherwise, again, this is like a orthogonal projection operation, which is another way of saying that we are minimizing this y minus t whole square, okay, through this orthogonal projection, and the projection matrix is given by this hat matrix of the feature vector, okay. So we are sort of computing the projection of t onto the space spanned by this feature vectors, orthogonal basis vectors, okay. So that is how we interpret. So this is a very, very nice interpretation that you can get for this particular thing, okay. Okay, so what happens if you don't have so there are two things you can do. So if this so here there is a slight change of notation, so phi has become a, but you can see what happens if your this A matrix is A transpose A is not invertible. So you can do two things. You can either add a small, like some lambda times I here, which we'll see it has also other interpretations, okay, but and then you still use this equation, okay, and we know that I is anything. So this A transpose A is a positive semi-definite matrix, so this plus I is always going to be invertible, okay, or use something like a gradient descent. So you can start from an initial beta, okay, in this case we are calling W as beta, okay, and then we can do this gradient descent step. So what does the gradient descent do? So the gradient descent basically, so your this j is the objective function which we called earlier ed, okay. We differentiate this j with respect to beta, okay, and that gives us the gradient vector of this j, which is the ed function that we saw earlier, okay, with respect to this beta, okay. And now we can simply take a step in that direction, okay, and if we run many times this, we can get the optimal beta by solving this, okay. So this is the gradient descent, okay. So we have talked about algorithms for estimating W, and we have seen two algorithms, one which we can use directly and one which we can where we have to use this iterative gradient descent algorithm to solve it, okay. Now let us see what it gives for the data set that we described. If you remember in the first slide, we described this data set where we have this sinusoid function and we have this input data point, okay. So first we try to fit a 0th order polynomial to it. 0th order polynomial is basically a constant function, okay. So it fits this red line, okay. Next we try to fit a first order polynomial. First order polynomial is any line, okay, any linear function, okay. So it is basically, if you remember, W0 plus W1x is what is the formula for this line, okay. The other one is just W0, okay. Okay, if that is the case, we get this particular line, okay, fine. If we try to fit a third order polynomial, we get a surprisingly good fit, okay. So you see what we are trying to estimate is this green. We know here because we have generated the data from this green. So the way we have generated data is exactly the mechanism that I just described, okay. Okay, so here this red this red is the estimated third order approximation to this particular data, okay. Now what happens if we increase this m? So if we use more and more basis functions, okay, we see that we get this red fit, Okay, we will get this kind of a red fit. Okay, now this is a very bad fit to the green one. Okay, but if you see, it is exactly predicting the training data points. Okay, so the training set error is 0. Okay, so it is exactly predicting the blue data points, training data points. So the training set error is 0, but we know from visual inspection that it is a very poor fit for this green data point. Okay, so what is the problem? Okay, this problem is called overfitting. Okay, and so the question is, how do we detect this problem? Okay, so the way to detect this problem is using something called a test set or a validation set. So up till now I have only talked about one data set, which is this blue data points, which we are using for training. Okay, in addition to this, we will need other data points which are following the same distribution. What does that mean? That means that they have to be generated by the same process. First, you have to generate a point from this green line, and then you have to add a little bit of a Gaussian noise. Okay, so they have to be generated by the same process, but they cannot be the same test point. Okay, so then you will maybe get some points here, 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 something like this. Okay, so not the exact blue points that are here. Okay, then you compute the error on that also. So what is happening? The error on the training point, which is the blue line here. So here x-axis I am plotting the dimension. Okay, this is also sometimes in machine learning literature called model complexity. Okay, and we see that the training set error has become exactly 0 when I tried to fit this 9th dimensional polynomial. Okay, but the test set error has shot up. Okay, so there is another test set that I generated from the same data, and this test set error has shot up. Okay, this phenomenon is called overfitting. So when training set error is decreasing, or training set error is going down or has gone very low, okay, but test set error has actually shot up. Okay, so that means this is definitely not a good basis to select. Okay, yes.
So isn't this case of overfitting just kind of similar to what you mentioned when you were explaining the graphical interpretation of grade, like that thing? In the graphical interpretation, you had mentioned that when T itself was falling under the span of the S things, it was just basically you were getting like 0 test error back.
Right. You mean this particular
yes.
thing, right?
Yes.
No, here it's a different thing. Here, see, it can so happen. So one thing you are right, that in this particular case, also the test set error has the training set error has become exactly 0. Okay, but it does not mean so it cannot be said that one implies the other in either direction. Okay, so if the training set error could have become 0 simply because this features are such, okay, that this T lies in the feature space. Okay, and it is not overfitting. That could have also happened, I'm saying. Okay,
So it may happen that T happens. It may happen that our M dimension, the dimension that we're choosing is so high that it is spanning through T as well, or it may happen that the features of T are such that it happens to fall in the same like space. That's what you're saying.
no. See, I could have chosen 3 features here. Okay, and still T could have fallen in the subspace. Then training set error will be 0.
Yes.
But it is not overfitting. Clear? In this particular case, it's a different thing. So what I'm trying to say is that you cannot say that just because training set error has become 0, it is overfitting. That you cannot say. Okay. if your training set error has become 0 and your test set error is also very low, then it is not overfitting, and that can happen.
So both, so training has to be low and test has to be high for it to be.
Right. Okay, so that is the idea behind overfitting. Okay.
So there's a question from online. Mr. RK Goel is asking, I am unable to understand that how to select the initial basis function to continue with minimalization stuff. Can I devise my own basis function? What I understood is that before curve fitting, given data has to be transformed by the basis function.
Right.
This is his question.
Right. So see, that is a very good question, and that is so whole of machine learning is all about that, and we will see lots of basis functions and how we can select different basis functions. Okay. In fact, I mean, we will talk about deep learning where we don't design basis function. The neural network actually designs the basis function. It also designs the basis function all by itself. Okay. So we will see all those things. But that's a good question. So machine learning is all about that, how to select a good basis function. Okay. And so right now we have just mentioned a few basis functions which are commonly used with linear models. So just to step back a little bit, the reason we are discussing linear models today is that these are some of the simplest form of models. Okay. So these are not what I would say the state of the art machine learning methods, that is the latest and greatest. No, they are not. Okay. But they are very, very widely used. So they are, first of all, very tried and tested. So people have been using this for a long time, and they have been working for a lot of scenarios. Does not mean they will work in every scenario, but they have been working for a lot of scenarios. Okay. And there is very good theory. I mean, there are very good both tools and theory available behind this. Okay. And these are very easy to fit also. Okay. So that is the reason why we are discussing these basis function models. But one of the drawbacks of these linear basis function models is that we have to have some idea, some intuition, some idea, as in the person who is deciding the method has to have some intuition about the basis function model.
He's again asking how to ensure that basis function is not going to appear, going to alter given data points. How to ensure that basis function is not going to alter given data points.
Okay. So basis function is not altering anything, right? So what is basis function? So if you see this basis function is simply computing some features. Okay. So the way to think about basis functions is these are functions of the input data. So input data is remaining as it is. You are computing a function of the input data, and you can compute as many functions of the input data as you want, right? So your input data is what here? For example, take this particular example, right? So x is your input data. So if you did not use any basis function, x will be the only input. Okay. But since you are using basis function, so what are the inputs that you are getting? You are getting 1, x. So x is part of the input. Okay. But you are also inputting x square, x cube, and so on and so forth. Okay. So it's the way to think about basis functions is that these are, and you can also have polynomial basis functions and then supplement it with some Gaussian basis functions and then supplement it with some sigmoidal basis functions. All these are possible. Okay. It's not that if you are using one basis, you have to stick to that basis function only. Okay. Okay. So, yes.
Right. So two questions. First, we chose the test function to be what? Sinusoidal, the green curve.
Yes,
So
the
how do we choose that?
original function to be sinusoidal, yes. Not that, yes, you can call it the test function, yes, but this is the original distribution, yes.
So how do we choose that? How do you know it's not more or
nothing.
less
I have
complicated
just
than that?
generated this data from this. I mean, it's just for illustration purpose.
But when we are working with a real world data set, then how do you know what to compare it with to see if what we are generating is overfitting or not?
Very good point. Okay. So, so the question is that, how do we know? So if you, okay, so let me come back to this slide. Yeah. So you see, when we are showing this plot, what are we measuring? We are measuring the error on the training set, which is the blue curve, okay? And we are measuring the error on the test set, which is the red curve, okay? So the question can be that how do I know the test set? Okay, I know the training set, but how do I know the test set?
Yes.
So the question is, so what happens in practical situations? Suppose you don't know the underlying function, then you are given the a particular data set. Okay, so what you do, you split it into training or test. That is the simplest way to get both a training set and a test set. So you need two sets in order to do this analysis of whether it is overfitting or not. You need two sets, that is for sure. Okay, now if you don't know the underlying data, which is the common case, we will not know the underlying data, then whatever data you are given, you have to split it into two parts at the very minimum. There are also other things we will talk about, which are cross validation and all, but basically at the very minimum you need two data sets. Clear? So I hope that answers your question, right?
Okay. Second question was actually, do you need to? Can it be that you only have the training set and you just look at how complex it is and say that if it's more zigzag than this threshold, then it's overfitting? Can you say that?
Okay. So the question is, can you? Okay. So let me take that question a little bit later. There have been, so statisticians have been trying to design these methods for doing that. Okay, for a long time. Okay, but none of them are foolproof, and I will tell you the reason. The reason. So. So the reason they are not foolproof is because any such metric that you try to do. So let me also try to tell what is going on here. Okay, so what happens is, as this M increases, remember I mentioned that this is like a metric for the model complexity. How complex a model am I fitting? Okay, I haven't told you still now that why. So you can intuitively see that here, whenever I'm choosing 9, okay, I am fitting a more complex model than because I am fitting model with more number of parameters. Okay, so and actually a superset of parameters. So a model with M is equal to 6 has all the parameters that a model with M is equal to 5 has, and one extra parameter. So it is very clear in this particular setting that you are actually increasing the model complexity. Okay, but in all cases it will not be clear. Okay, so for example, I can just ask you this question. Okay, so I have told you about Gaussian basis function and polynomial basis function. So suppose I give you these two models, right? In one case I am using 10 polynomial basis function and no Gaussian basis function. Another case I am using, let's say, 6 polynomial basis function and 6 Gaussian basis functions. Which model is more complex? Can somebody tell me? It is not possible. Okay, so there is no, so the moment you have like practical problems, a proper measure of model complexity is very difficult to come up with. Having said that, people have come up with some measures of model complexity, and those can be used for model selection also without having to resort to a validation set. Okay, but yeah, the caveat is that there is no guarantee that they will work. Okay, so let me come to with that a particular measure of model complexity which people try to use. Okay, and let me try to motivate this by showing the coefficients. So here are some of the coefficients. Okay, so when M is equal to 0, this was the coefficient that was fit. Okay, when M is equal to 1, this was the coefficient that was fit. M is equal to 3, this was the coefficient that was fit. Okay, M is equal to 9, you see these were the coefficients that were fit, and you see these are ridiculously high value, and also you see they are alternatively negative, positive, negative, positive like this. Okay. So what is happening? Basically, as you go to higher powers of x, all of them are going higher and higher. Okay. And they're trying to capture some kind of a little bit of a, your model is trying to capture a little bit of a signal here. Okay. And in trying to capture that, it is taking x. So this is x to the power 4 force coefficient. So it is saying 2 lakh times x to the power 4, or minus 2 lakhs times x to the power 4 plus 6 lakhs times x to the power 5. Okay. So it's capturing signals like this, very, very fine signals it's trying to capture. And this is what is leading to the overfitting. Okay. So what they said, okay, that how can we, how can we, so we see that this is what is happening here actually. So the W vector, the magnitude of that is ridiculously high. Okay. So can we not just penalize the magnitude of the W vector? Okay. Can we not say that if norm of this W vector is very high, then I am fitting a high complexity model? Can I not say that? Okay. If that is the case, okay, then what do I have to minimize? I simply, so this part is the squared error, the first part. Okay. But along with that, I am adding this norm of the W vector. Okay. So, and I'm adding this lambda, and again by 2 is just so that when you differentiate, it does not, so it's just for computational reasons. But this lambda is a user defined parameter which the user will provide at the time of optimizing, and the user will say that so the higher value of lambda will mean that I want to impose a higher penalty to this norm. Okay. And a lower value of lambda. So lambda, for all, lambda, let's have lambda positive, otherwise it does not make sense. Okay. So lambda will be a positive number that will be provided by the user. So lambda is not to be optimized with respect to. Okay. So the optimization variable is still W, but the user is providing a lambda. But now the optimization function has changed. We have added what is called a regularizer here. Okay. So this norm of W is called regularizer, or more specifically L2 regularizer. Okay. So that is that we are using the 2 norm of W for regularizing. Okay. And the weightage of that regularizer is given by this lambda, which is provided by the user. Okay. And the higher the value of lambda, so lambda is greater than 0. So if we provide lambda is equal to 0, then we go back to least square regression. Okay. If we provide lambda something very high, then this error term doesn't matter in that case. Okay. In that case, what will be the solution? What will be the optimal? W is equal to 0. So it's as if you have not seen the data at all. Okay. Your solution will be very close to just all the W's should be 0. Okay. So this is the case. Okay. And this is actually used very, very heavily. Okay. And let me see. Yeah. So yeah. So now, okay. So you may ask that at least in this particular case, what is the reason why you want to so by the way, this regularized least square is kind of the thing that is more used. So one of the reasons is that it's a generalization of ordinary least square, but there is a definite advantage to this regularized least square. Can someone tell what is the advantage of this regularized least square? See, the advantage is not mathematical. The advantage is, it's like from the user's point of view, it is very advantageous. What this regularized least squares is doing is it is decoupling the feature selection or the feature generation part. Okay. What is feature generation? Feature generation is this polynomial basis that you are selecting, or the Gaussian basis that you're selecting. That is coming from your domain knowledge. Okay, so for any practical problem, your features that you will generate will come from your domain knowledge. Okay, so you don't want to, worry about two things at the same time. One is, am I incorporating all the domain knowledge for my problem or not? That is the first thing that you want to worry about. The second thing that you want to worry about is, I should not be putting in too much domain knowledge so that I start overfitting. You don't want to worry about these two things at the same time. Okay, so what this regularized least square is doing is it's decoupling the two. One thing is that you select how much ever features you want to select. In this case, we have selected, so this is this example, we are going back to the same, with 9 features. Okay, m is equal to 9. Okay, but now we are fitting with the regularized least square with lambda is equal to, so here we are seeing maybe okay, let's look at this one. Okay, so we are fitting 9th order polynomial. Okay, and now what we are saying here is, on the x-axis we are now seeing what is the value of lambda. Okay, and you see we have a position here, so we still have to vary the value of lambda to actually get a good position. So what is a good position? So this is the training set error. Okay, so a good position is somewhere here or maybe here, where lambda is maybe log of lambda is maybe minus 20 or something. Okay, sorry, minus 32 or something, where you see your training set error is also low. Okay, and your test set error is also low. Okay, yeah, so there is sometimes people also measure the gap. Okay, but anyway, that's a different story, but visually at least right now you can see that this is probably a good operating lambda. Okay, and this you are able to select just by varying lambda. You don't have to change the features that you have given as input to this problem. So okay, so so this is called regularized least square regression. And then yeah, so in general it will be something like, there is a data term which is dependent on the data, and there is a regularization term, okay, which is dependent only on the parameter value. Okay,
Sir, there is again one question from RK Goyal.
Hmm.
Can we penalize it for further by using L3 norm on what is the right value of the norm and why to include lambda?
Right. So let us come to that. So in a minute. Okay. So two things. I think first of all, how to compute lambda you can understand, right? So if you, so from this I think it is clear how to get to lambda. How do you get to lambda? You use the same thing, the test set error, okay, or the validation set error. So the lambda for which the validation set error is minimum, you choose that particular lambda. Okay, so you choose different values of, so you search over lambda, you choose different values of lambda, you train the model. Okay, so first of all you get all the features that you can. Okay, you choose different values of lambda, you train the model, whichever gives you the lowest test set error, that is your best value of lambda. With that value of lambda, you train the entire model again with on the entire data to actually get the correct this thing. Okay, so this is the one part of the question, I think. We are searching, yeah. So yeah, we are searching over different lambda. Yeah.
So
So-
I have a question, may I? During overfitting, we have seen that it was amplifying the high frequency signals. Why does it happen at first place?
Yeah, so actually this high frequency signal again is like, okay, so you're talking about temporal domain signal, right? Higher order polynomial, yeah. Okay, so are you asking for this particular thing, why it is happening? Oh, okay. So in order to understand that, you have to see that. So what it is doing? So see, already the lower order polynomial values, okay, they have captured most of the signal. They have captured. They are able to predict pretty well. Okay. Now what this guy, but your training set error is not zero still. Okay. So think about it something like this, that using whatever 3 or 4 polynomials, it polynomials, it has tried to capture the signal. Okay. And then there is the noise part. Now the noise part has to be fit. Okay. So whatever signal is left will be used to capture the noise. Okay. Now the question is, why is this coefficients high? Okay. Why are these coefficients high? Okay. The reason is that so if this is not high, okay, uh, uh, so this has to I mean, how should I put it? Um, uh, so both x to the power 4 and x to the power 5 are capturing very similar things. Okay, so these are highly correlated features. Okay, so I can maybe explain with another example. Okay, so what happens if I give two features which are exactly identical? What kind of coefficients would you expect to learn for these features? One answer is same. Any other answers?
Are you hinting at this thing? They will predict similar values but opposite in sign.
Right. So what is seen is that if you don't regularize, what will happen is, see, it's trying to, like I mentioned, right? So it's not getting the zero error, okay? And it has got these two features which it can bank on, okay, to try and fit the noise. So what it will do, it will increase the weightage of, so think about it, I mean, think about the machine doing like a trial and error. So it will increase the weightage of this feature, okay? The overall prediction will go somewhere. It knows that it has this, feature to balance it out. So it will also increase the negative weight of this feature. Okay, so it's like that. Okay, of course, I mean, it depends. I mean, this is like an intuitive explanation that I am giving. Okay, yeah. Okay. Okay, I think this one is clear. Okay, now you see this, that okay. So so here one thing I wanted to mention, that if you use this regularized least square regression with non-zero lambda, then you can always use these normal equations. So these are the normal equations that I was talking about. Now the regularized version has a lambda I added to phi transpose phi. Okay, and this is always going to be invertible. So you can always use. So that is one added advantage of using regularized least square with a non-zero regularizer. Okay. Okay. Now comes the second question that was asked, which is that why are you using this q is equal to 2? What kind of q should I use? Okay. So in practice, we have seen that q is equal to 2 and q is equal to 1 are two very good regularizers. So as you change the value of q, the properties of the regularizers change a lot. Okay? And here I am just showing the equipotential contours of the different regularizers. So q is equal to 2, you can understand that all these w's have the same value of norm of w, right? So it's a circle. Okay, q is equal to 1, this is the equipotential contour. So you have like a diamond. Okay, so between this and this, you can just draw a straight line, and all of those guys will have the same value for norm of W. Okay, and so on and so forth. Okay, so these are the equipotential contours. So as you go more Q, it becomes more bulbous kind of thing. As you go less Q, it becomes like this. Okay. Now Q is equal to 2 gives us the regularized least square, and it does what we have shown already, that it tries to control the overfitting. Okay. Q is equal to 1 gives us a sparse solution. Okay. What does that mean? So basically, think about it like this, that you remember that your regularized least squares, okay, there are two objectives. One objective is trying to make W 0. All the norms, the if we don't have data, the objective function value is going to be 0. Like the optimal W is going to be 0. Okay. So one of them is always, no matter which Q you use, it is going to try and make W 0. Okay. And the other one is this. So this is the optimal of the ordinary least square solution. This is also, so this I have shown here circles. This could be ellipsoid. This normally will be all ellipsoids. Okay. But nonetheless, it will be a convex region. Okay. So there is this tug of war going on between the what W is the optimal. Okay. And it is kind of at the intersection of these equipotential contours. Okay. And now you see where the intersection is happening. Intuitively, I am just telling here. Here, the intersection is happening at a point where both W1 and W2 have some values. But here, with high probability, unless this point is somewhere exactly at 45-degree angle, or very, very somewhere very close to here, with high probability, it's going to intersect at one of the vertices. Clear? Which means the other W's are all 0. Okay. So that is why it is leading to a sparse solution. Okay. So these are the two widely used things, and a combination of these is also used, and I think I have a example of that also, which is called the elastic net, where you can use like something like a lambda 1 times L1 norm of W plus lambda 2 times L2 norm of W. Okay, that can also be a regularizer. Okay. Okay, so this finishes the regression. Let me just can I switch to the so I want to do two things. So before I do classification, I can just give some demos of the lab, and then we can go to the classification. Is that better, or should I go through the slides and then go to the demo at the end? I mean, which one do you guys think you guys will be? Okay. Yes.
Question is, sparse solution is the solution with most differential features.
So obviously, yeah. So if you are selecting a few features, okay, it's going to and it has to obviously fit the data, training data. So it is going to select the most influential features, right? So yes, yeah. So I would say most predictive features. Okay, so there's a critical difference between them. So it's not always that the most influential feature is also the most predictive feature. Okay, so yeah. So I would say, and so yeah, so and this is a very, very complicated topic that one can go into. I mean, basically what happens is that you can sort of so you can have a most influential features which does not have a complementary feature to it. Okay, so then that single-handedly that feature is most influential. Okay, but maybe 2 or 3 of the other features together are better predictive than this most influential feature. Okay, so anyway, yeah, that is the thing. Yeah. I can try to run that Google Colab.
Your system can do that. So that will be better.
Should I do that? Will that be visible online?
We can try, right? In that it is fine, right? Google Colab that works. We loaded it. Control L. But everyone can join online. So, sorry. If you are working in your system, everyone is joining online. They can also get that.
Oh, I can join the meeting from there itself. That's what you are saying. Yeah, that is also a good idea. Yeah, actually, that's a very good idea.
It's normal like online.
Like I will join the meeting from this system, but you have to connect me to proper internet in that case.
So I think we should announce for a 5 minutes break now.
Okay. Yeah, sure. Let us take a 5 minutes break and then we'll come back in 5 minutes. USB এখানে আমার ওটা ইয়ে করা আছে। Okay. Hello everyone. So welcome back. I hope you can hear me. Everything is fine. Okay. Okay. So one announcement is that the files that I am going to be using for this demo, they have been uploaded here. Okay. So if you go to this sesi.in/AIML space weather, okay, and if you go under this heading workshop tutorial materials, okay, you are going to see this link 28
Sir, good afternoon. Sound is not
2022.
coming properly.
I hope my screen is also visible. Okay. And then if you
Sound
click
is
on
not
it,
coming.
you can get the files. So let me just show the files. Yeah. So yeah. So you should be seeing two of these IPython notebooks, linear regression, linear and polynomial regression .ipython notebook, and this regression hyphen real hyphen data IPython notebook. Okay. And you will need some of these data files. So you will need, I think, maybe this auto mpg
Your sound is
and
not coming.
airfoil data. Okay, these two are
Hello.
these are standard data sets. Okay,
Hello.
which you will be
Your
needing.
sound is not coming.
Yeah, it is. Hello. Yeah, it is fine. Hello. Okay. Okay. So then let us start. So so I am kind of assuming that all of you are familiar with Python. Okay. So I am using this IPython notebook. Okay. So the first cell, I am just imposing some libraries. So the first library is NumPy. Most of you may be familiar with it already. It's for numeric computations, and it is kind of one of the main libraries that we will be using. Another very important library is this Matplotlib library. So matplotlib.pyplot, and this is for plotting all the all the visualization and everything. Okay. And then there is this scikit-learn, which is the main library that we will be using for doing machine learning. Okay. And yeah. So so the library is basically sklearn, and sklearn has many modules. Okay. So you can see that I am importing the linear model module because that is the main module that I will be using. Okay. And this R2 score module from sklearn matrix I have used, but this is something you can also write yourself. I mean, we will go over it a little bit. Okay. So for those of you who are not familiar with how machine learning works, okay. So here basically, so you can do many experiments. Okay. So the first experiment, I'm just going to show how a simple linear regression works. So these are the steps. So first we will generate synthetic training data. Okay. Then we will visualize this data. Okay. Then we will fit model with scikit-learn. Then we will observe the errors. Okay. Then we will calculate mean square error. Okay. And then we will generate synthetic test data. Then we'll observe the test error, and we'll also calculate different types of errors. Okay. Okay. So first I'm just generating 40 training data points. Okay. By the way, you can just run this if you just simply press shift and then enter, you can run the cells. So I was just running this first cell, then second cell. Now I have come to the third cell. Actually, all this output is there because, so let me just actually, I can clear all the output also. No, yeah, 1 minute. Yeah. Yeah. So okay. So now there are no outputs, as you can see. Okay. So I'm just running this here, and it will generate the output. Okay. So the first computation here is that I'm generating the data. The way I'm generating the data here is that I'm generating data between 0 and 1. So NP linspace is this NumPy library or NumPy function, which is generating n points, many data points from 0 to 1, between 0 and 1. Okay. So you can also see the signature. So it's like start, stop, and then other things. Okay. So yeah. Okay. So you can see the whole thing. Yeah. Start, stop, and then number of points, and then there are some extra other things that we don't need to currently worry about. Okay. Okay. And then here I'm just reshaping X. Okay. To so actually this linspace returns one-dimensional NumPy array. Okay. So I'm just assuming that everybody is familiar with NumPy. Okay. So please ping if you are not. And then I'm just reshaping here simply to make it two-dimensional array. Okay. So that X is two-dimensional array. We need that. Okay. And then I'm generating this data. So this is just a linear data. So I'm just multiplying X by 30, and then I'm adding this random normal a random sample from normal distribution with zero mean and unit variance. Okay. And then I am generating the number of such random points I'm generating is given by this size, which is of the same shape as x. Okay, so so I'm generating that many, and then I'm adding to x, and then I'm generating y here. Okay, so if I do this, you can see, you can see the data like this. So you can, so this is one way. I'm just doing a column stack so that you can see the data together. So this is the x and this is the y. So x is 0, y is this much, and so on and so forth. So this has the noise added, so you can see this. Okay, but this is not probably very meaningful. This one is probably more meaningful. So here you can see a plot of the data. Okay, so what I'm doing, I'm using this, this Matplotlib to plot x and y, and this is with blue and round points. Okay, and then I'm just showing. So here x-axis is x and y-axis is y, and you can see that this line is something like this, where you should be getting 30 times x, y is equal to 30 times x. But because I have added some noise, it is showing a somewhat zigzag line. Okay. Okay. So now, next, I'm going to just fit the model. Okay. So for that, I'm getting this regression model. Now, this regression model is something that I am getting from this linear model package. Okay, so scikit-learn has many different modules rather. Okay, so linear model is one module that scikit-learn has. Okay, and in that we have this linear regression model, and we are getting the getting an instance of this linear regression model through this function. Okay, and I can pass some of these things, like I can pass fit intercept or other things, but I'm already, it is fitting intercept, so I'm going with the default values. So if you see this fit intercept is true, normalize is not needed, and so on and so forth. Okay. Okay. So once I get this model, so up till now you can think of it as the parameters of this model are random. Okay. So next step, I say that I am fitting this model. So I am fitting this model with x and y. Up till now, I did not provide the x and y. By the way, x and y, if you recall, is the data. That is how I generated the data. Okay, and I have visualized this data also here. Okay. Now, when I pass x and y, it fits the model, and you can see that fitted model like this. Okay, so you can say that there are these parameters. So one is the coefficient. So reg model dot coef underscore, this gives the coefficient. Okay, and reg model dot intercept, this gives the intercept. Okay, and there's not much intercept, so the intercept value is just minus 0.4. And here I see that coefficient value is about 30.7 or something. So very close to how we generated the data. Okay, so it is able to satisfactorily learn it. Okay. Next, what we are doing is we are using reg model dot predict and then passing only x here. Okay, so we are only passing x here, and we are calculating what is called the y hat, or the predicted y. Okay. Okay, so y hat contains the predicted y. Okay, and now we are trying to plot here the training data and the predicted data in the same plot. Okay, and this blue one is the training data. Okay, and the red one is the predicted data. And as you can see, the red one is actually tracing the mean of the blue line, because the blue has the noise inbuilt in it. Okay, so it's tracing the blue curve very nicely. Okay. So yeah, so I'm just I'm assuming that the code is clear. Okay. Okay. Now next comes the calculation of error. So remember, I am doing all this on the training set. Okay. So first I am calculating the error vector. So this can be either positive or negative, and this is y minus y hat. Okay. Then I am calculating the mean squared error, which is nothing but sum over the training set y minus y hat whole square. Okay, and this is like this can be computed using I have used here np.matmul np.transpose err times error, but you can also use numpy.dot or something like that. Okay, I'm just showing some of the numpy things. Okay, and then you divide by the length of error. Okay, another important thing people use is root mean square error, which is the square root of mean square error. Okay, now another thing people use is what is called the mean absolute percentage error, or even more so sometimes people also use so this is called MAPI, mean absolute percentage error, or sometimes people also use SMAPI, which is the symmetric mean absolute percentage error. So what is this? This is basically you take the error and divide it by the true value. Okay, so this I'm talking about MAPI. If you have to use SMAPI, you have to take the error and divide it by the average of the absolute values of the true value and the predicted value. Okay, so in you can think like if true value is y and predicted value is y hat, let's say. So here we are doing y minus y hat by y. Okay, and then absolute of that. In MAPI, in SMAPI, we would do y minus y hat by absolute value of y plus absolute value of y hat by 2. Okay, so this is what we will do. Okay, and then we take the average of that and multiply by 100 because we are taking percentage here. Okay, and then we are so this is so the advantage of this MAPI or SMAPI type thing is that unlike root mean square error or mean square error, okay, this MAPI gives you a percentage error. Excuse me. Okay, so this gives you a percentage error in terms of what I mean. So in case of MAPI, it gives you a percentage of the actual value. In case of SMAPI, it will give you the percentage of the average between actual and predicted value. Okay, so that is the advantage of MAPI or SMAPI over the mean square error. Okay. Another advantage we can say is that in case of mean squared error or RMSE, it generally tries to blow up the higher errors. Okay, because you are taking square and then adding up, and they can then taking square root. So it tries to blow up the higher errors compared to the lower error values. Okay, so that may be good or bad, but these are the properties. Okay, so on the other hand, this coefficient of determination is another very nice metric. So what this does is basically it computes the so it computes the error. So it is something like 1 minus the error divided by the variance of the true label. Okay, so in other words, so 1 minus numerator is error squared actually. Okay, and denominator is y minus y bar square. So numerator is y minus y hat square and denominator is y minus y bar square. So what this captures is this basically captures the error as a fraction of the total variation of the value of the predicted variable from its mean. Okay, so that is the coefficient of determination, and both MAPI and coefficient of determination are very, very widely used. Okay, so here you can see that it is showing a MAPI of a training set MAPI of 22%. Okay, and so coefficient of determination is the maximum value can be I mean 1. Okay, unless you are doing very, very horrible predictions or something, it should not yeah sorry yeah, so minimum so maximum value anyway can be 1. Okay, but the minimum value can go below 0, but typically it's between 0 and 1. Okay, so yeah, so if coefficient of determination is close to 1, then you are doing pretty fine. So here we can see that coefficient of determination is about 0.98. Okay, so this is all about the training set. Okay, now here in this particular thing, we are now generating the test data. Okay, so earlier we were generating the training set data, which was blue, and now we have generated test data. So training data was from 0 to 1. Now test data I have generated from 1 to 2. Okay, I have generated this test data from 1 to 2, and again 40 data points I have generated. Okay, and then same thing in the same manner. So you can see that it has noise, and it is using the same generating mechanism. Okay, now I am simply using here y test hat. So for test data I am not doing any fit, I am simply doing a predict. Okay, and I am passing x test here. Okay, and then I am getting y test hat, and then I am also predicting for y test. So this is the prediction, and you can see that again it is kind of, so here this should not be training data, this should be test data. Let me just change it. So this will be test data. Okay, and this red one is the predicted test data. Okay, okay, so you can see that this is the predicted test data, and blue one is the test data now here. Okay, and we are doing a decent prediction, but now let us do the same error calculation. Okay, let me just copy paste this R2 thing also here. Okay, coefficient of determination score. Okay, and I have to pass here y test and y test hat. Okay, and then I have to print here coefficient of determination. Okay, so you see everything has gone down a little bit. Okay, so earlier if you see the MAPI was about 22%. Now for the test set, okay, something is wrong here. What is wrong here? Error and y. Okay. Yeah, something is not right here. This should be something like a 25%, I think. Okay, so let us not look at the MAPI. So you can see that mean square error has also gone down a little bit, gone up a little bit. So here it was 0.8 and 0.9 RMSE. Here it has become 1.6 and 1.2, and your coefficient of determination has also become 97%. Okay, so MAPI calculation, there is something basic is wrong. Yeah, we have to see this, but anyway, so this is what it is. Okay. Okay, so this is all test set numbers. Okay, so this is all test set numbers. Okay. Okay. Yes. It does not have to be, but that is the normal thing to happen. I mean, otherwise it can be. So
We're just getting like errors from a Gaussian distribution, right? So from a normal distribution. So it might so happen that in the test set we're actually getting data that fits more into our actual like predicted model than the training does.
it can be, yeah, absolutely. So it doesn't have to be that it will always be the case that test set error is less, but test set error is more. Um, but you should be a bit wary. So when you are writing the programs, see, typically what happens is we make mistakes while writing code, right? So you should double check why it is. If it is not happening, then you should double check, because the thing is that you are explicitly fitting the training set. Okay, you are not explicitly fitting the test set. Okay, so if you are
I think we would get better results if we actually ran this a couple of times and then we took the RMS of that error. Value.
Yes, of course. So if you are doing random data generation, or if there is any kind of randomness, you should run it a couple of times and check. Yes.
Because in my case, I'm getting all errors reduced by a margin. So my RMS is coming around 81%, 0.81. So
okay, you are running the same thing, and then you are getting.
So basically, since we're synthetically doing it like separately every single time, I created another set. I ran it some number of times, and in this particular iteration, it just so happened that the RMS became much less than the RMS for the test. RMS error for the test was much less than the for the training.
It can happen. Yeah. You are right. So it can happen for some particular test set. Yes. But that is a very what should I say? Very
rare case.
Yeah, it's a very rare instance.
Because my coefficient of determination came around 0.9914.
For that, okay.
Yeah.
Okay, but that is so if you run it a couple of more times, it will typically not be the
Exactly.
case.
So over more iterations, we'll see a trend of the test data showing more variation than the training data set.
Okay. Yeah. So now there is so this was the first sort of experiment, simple experiment to get us all started. Okay. So now we go to that polynomial regression experiment that we were thinking. Okay. And now we are doing the same thing. Okay. But now we are generating this x. Okay. But this time the true data is I'm generating from sine of x. Okay. So I'm saying y is equal to np or np dot sine of x plus the same noise. Okay. And you can see actually here the noise is a bit more than so it may not look exactly like sinusoidal also. Yeah, probably this one. So if we generate let me generate this with yeah, so now it is looking a bit more like a sinusoid. Okay, let me generate this with 10 maybe. Okay, so if I generate this with noise of 10, you can see that it's a sinusoid but corrupted with noise. Okay, so this is what my data is, let's say. Okay, now what I do, again I do the reg model dot fit and then I do the predict. Okay, so okay, yeah, but now here you remember, so I'm doing a fit and a fit with basically x, so it is taking something like, so its model is w0 plus w1x, right? So it is fitting a straight line. Okay, and if it is fitting a straight line, then it is basically getting this particular straight line. So let me just join this once more. Yeah, so it is getting this red straight line, that is the fitted data. Okay, and it is doing a bit of a fit but not very good. Okay, now what can we do? So we can generate this a certain number of degree features. Okay, so how are we generating? So we are saying this x, so by the way, this can also be done by some of the library functions, but I thought, just wanted to show that you can just write small amounts of Python code and also do it. Okay, not a big deal. So you can just say that x trans is the transformed x. So this is basically my Phi matrix. Okay, and then I initialize with np.ones. Okay, and then for I in range 1 to degree plus 1, okay, basically this will go to degree because it goes to 1 less than the last guy. Okay, you do x trans is equal to np.concatenate and then x trans and then numpy power x comma I. Okay, so you are every time you are so first I is 1, so you are concatenating the x to the power 1 features to the earlier all ones feature. Okay, and then you are concatenating the x to the power 2 features and so on and so forth. So when you run this, yeah, so I'm just showing all the features. So you see, as x is, so here x axis is the x and y axis are the transformed features. So this is basically showing the polynomial kernel. So the blue line is degree 0 is all ones. Okay, the red line is degree 1, the green line is degree 2, the black line is degree 3. So you are seeing all the different degree features. Okay, and now with this modified features, you can see that I can fit this. Okay, so let me try and now fit some more features like some higher degree. So I try to fit 10th degree thing. Okay, so here it will show only till 3, but it has actually generated 10th degree features. Okay, and here if I run it, yeah, so you can see the coefficients. Okay, and you can see that it has already, because I don't know how many data points did I have. I had yeah, 10 points. Okay, so I had 10 points and actually it has done a pretty good fit for some reason. Okay, possibly because even if you do a linear regression, okay, it does a tiny bit of regularization. Okay, so maybe like 10 to the power minus 10 or 20. So it has done a very good fit. Okay, yeah, so in this case it has done a very good fit, but yeah, you cannot say that about always. So let me try and see if I try to fit a 20 degree polynomial, what does it do? Okay, I have generated the thing. Yeah, now you see it has done all some weird kind of fit. Okay, and by the way, here I am showing all the coefficients, and for some reason the coefficients are all coming out to be very small here. Okay, okay, let me actually change the data a little bit. Let me add a little bit of more noise to it. So I reduce this. Okay. Yeah, still it is able to track it pretty close, because I think the fit is doing a tiny bit of regularization here. Okay, but yeah, so anyway, so this is just to show that you can play around with this code to fit basically a polynomial basis function model. Okay, so any questions or comments with this? Okay, good. So now, see, one of the things I wanted to focus today here is how to run this thing on real data sets. Okay, so and it's not much of a mathematical thing really. Okay, but one of the main challenges of running anything on real data sets is that you have to do the data handling. Okay, and it is a practical challenge. It's not, it's a programming challenge. It's not so much of a conceptual or mathematical challenge as a programming challenge. Okay, so so I just wanted to talk a little bit about that. Okay, so how do you so what we are going to do, so I have taken these 3 data sets here. So the first one, I mean, let us focus on the first data set, and other 2 you can just simply work. You can just work on the same lines. Okay, so the first data set is this auto Mpg data set. You can see it is a data set from CMU Matplotlib Library, and it concerns the city cycle fuel consumption of certain automobiles. Okay, so these are the steps. So we are going to basically read the data from a file. So the data is already there in a file. I will show you in a minute. Okay, then we will see that we will try to remove some records which have a missing data. Okay, then we will so this is the first thing. The second part is that many of these data sets will have categorical attributes. Categorical attributes are attributes with discrete values. Okay, so what you have to do when you are training linear models, or for that matter most of the machine learning models, okay, you have to transform these categorical attributes to binary attributes. Okay, so you can do that, and then you can create a numpy array, and then the rest of the procedure will follow as before. Okay, so yeah, so I'm just so one extra library I will be needing here is what is called the Pandas library, which is used for reading the data and pre-processing the data. Okay, so so this is the data set. Okay, auto Mpg. Okay, and then what we are doing here is we are basically so the data set has these attributes. I think there are 8 attributes: 1, 2, 3, 4, 5, 6, 7, 8, and 9 attributes. And the last attributes is a string, which is the car name. Okay, so actually this is the command that we use to load the data. So the data is on my local hard drive, and this data has been shared with you, or you can download the data from the URL that is mentioned. Okay, you have to give the path to the data. Okay, now in this particular case, I have seen that the separator is a space. So if the separator is a space, then you give this \s plus here. Okay, then you have to give the names of the columns. Okay, so I have the names of the columns here from the data set itself. So I'll just give the names of the columns: mpg, cylinders, displacement, etc. Okay, and I have to give this header is equal to none, just because otherwise by default Pandas will take the first row as the header row. Okay, so I have to give this header is equal to none. Okay, and let me just uncomment this so that you can see how it reads the data. Yeah, So it read the data like this. Okay, so so miles per gallon is 18, number of cylinders is 8, displacement, horsepower, weight, acceleration, model year, origin, and car name. Okay, so so it's read the data correctly. Okay, now up till now everything is fine. Okay. Okay. Yeah. Just to, that's the next thing. Yeah. Okay. So I'm going to go to the missing value analysis. Okay. So you have read the data now here. Okay. So now what you will do? So how will you you know? So what does it mean to say that you are going to do a missing value analysis? Okay. So basically what you do is you first do some basic data quality check. Okay. So one of the very basic data quality check is that you try to determine whether the so this pandas is this library, right? So pandas is reading the data, but you see it is also assigning types to each column. So that is one of the advantages of pandas, that it is not only reading the data, but it is also trying to automatically determine what type of data is it reading per column. Okay. So now using this df.d types, you can see the types of the data. Now you see Mpg column, it is saying float 64, which is the correct type. You expect the miles per gallon to be a float. Similarly, cylinders, you expect it to be int 64. So it's like an integer. Okay. So many of them it is fine. You see, for the horsepower, it is saying the type is object. Okay. Now, whenever you are seeing this type object, then you should be a little bit careful. Okay. So that means it is not determined as a floating point number or an integer number. Okay. But something else. Okay. So for car name, it is clear because car name is a string. So it is going to be detected as a string, and a string in Python is an object. So so that's understandable. But why is this horsepower also getting object? Okay. So then we know that. So if you see here, horsepower is numeric, right? 130, 165, and all this should be, you should be able to convert it to numeric. Okay. So let me just first try to run this with actually with errors is equal to raise. Okay. So you see, so what am I trying to do here? Okay. I'm trying to convert this horsepower column to numeric using this Python's to numeric thing. Okay. So you can see here the convert argument to numeric type. Okay. So that is what I'm trying to use here. Okay. Now I'm doing, I'm passing here horsepower. I'm just saying errors is equal to raise. So so that means if there are any errors in trying to convert horsepower, okay, then it should raise that error. Okay. I'm instructing pandas to do this. Okay. Now it is raising this error. You see, it is raising a value error in yeah. So it is raising a value error, and it is saying unable to parse string question mark. Okay. And it is also saying that yeah, so at position 32. Okay, so it's giving you everything. It's saying at position 32 there is a question mark, and that is why I'm not able to parse it to numeric. So that is why in the first place it was not detected as a this thing. Okay. Now let me say errors is equal to coerce. Okay, so errors is equal to coerce means it will not raise the error. It is still getting the error, but instead of raising the error, now what it will do, it will simply give a NaN value to those numbers where it is getting error. Okay, why am I doing this? Because then I can use this is null. Okay, so this is null property. Okay. to actually get the location, okay, and then I can also basically, so I'm getting this particular column of the data frame, and then I'm asking it which are the values that are null, and then I'm getting the values means indices of that, okay, and then I'm just printing those particular data, okay, or those particular rows from the entire data frame. So these are the rows, okay, 32. So the total number of rows here was 397, out of which these 32, 126, 330, 336, 354 and 374s, they have nan in horsepower, okay. So there was a missing data or a question mark in these particular rows, okay. So that is how you determine it, okay. So then you can simply, what you can do is yeah, okay. So so what you can do here is then you can use this drop NA function to actually drop all the null elements. So you can see here that okay, it does not show the, yeah, remove missing values, okay. So it says that remove missing values. So basically whichever are the null values, it will simply remove those records, okay. That is the job that this drop NA function does, okay. So it does that. So now you can simply see that it had 397, it has removed 5, now it is only 392, okay. It has only 392 entries, and yeah, so this is basically the 392 entries which it has, okay. Okay, now 392 rows and 8 columns, okay. Okay, so up till now everything is fine, okay. So we have removed the missing data now, so there are no more missing data, okay. Now we want to convert categorical to binary, okay. How do we convert categorical to binary? Okay, so first of all you have to understand, you have to have a guess that which one are categorical. So probably model year is a categorical attribute, and probably this origin is also a categorical attribute, okay. So if you see here, yeah, so yeah, see, this model year and these were discrete, okay. Number of cylinders was also discrete, but we did not remove it, that's fine, okay. But this model year and origin were discrete, okay. So but these have been detected as integers. So if you just, so actually the pandas function for getting binary attributes from categorical attributes is this get dummies. So you can see it says it, so they call it convert categorical variable into a dummy or indicator variable. So what it does, it takes, so categorical attributes will take a particular set of values, so it will create one binary attribute for each value of that particular categorical attribute, okay. So this is what it will do, okay. So let us take an example how this is working first, okay. Okay, yeah, so it got the dummies, okay. Yeah, so df dump, let me just let me just show you df dump here, okay. Yeah, so you see what it has done is it has created this model year. Model year had all these values, okay. So model year was 70, 71, 72 up till 82, okay, 70 to 82. So it has created all these extra 12 variables for model year, okay, and it has basically placed a 0 wherever there was 70. So it has for this attribute wherever it was 70, it has placed a 1, otherwise it has placed a 0, okay. So this is what it is. Similarly, origin had 3 values, 1, 2, 3, so it has created the corresponding indicator variables here, okay. So this is what it has done. Okay. So now we are all done. So we have the, the categorical to indicator conversion. We have removed all missing data. Okay. So now we just convert this dfdum to numpy. Okay. And then we pull out. So we know that the first one is the label, and 1 onwards, all of them are the features. Okay. So we just pull out the y and the features, and that is our y and x. And then we do exactly as we did. So we take the reg model, we fit it, and we predict. Okay. And we are doing first a scatter plot, and then we are seeing all the errors, and we are also going to see the error histogram. So let us see. Okay.
I have a question. So the getDum is that, does that only acts on string variables?
It acts only on string variables. Yes, yes. So
You are changing aspect.
yes. So actually, if you see here, it actually detected these guys as, so where was I there? Yeah. So origin and model year as int64. Okay. So if it is int64, it will not work. Okay. So because it will take it as numeric, and then it will not, basically it will convert the int64 to directly float.
So the cylinders, that is not treated as.
That is not treated as, exactly. So that is not treated as, the cylinders is not treated as dummy. Okay. So yeah. Okay. Okay. Yeah. And that also, actually, I have removed already the car name variable. If you see here, I have removed the car name variable. Otherwise, it would have treated the car name also as a categorical variable and then tried to create a dummy variable. Okay. So somewhere I have removed it. Yeah. I don't know where I have removed it, but I have removed it anyway. Okay. Okay. So let's go back to this thing. Okay. Now, so okay. So now here, so the first plot is just a scatter plot. Okay. So this x-axis is, let me just see. So x-axis is y, which is the true variable, and y-axis is the y hat. Okay. And if it is a 45-degree line, that would have been the best. Okay. There is some amount of scatter. Okay. So let us see how. You can see that there is a lot of over prediction actually here. Okay. So everything is being predicted higher than the 45-degree line, right? Okay. So the second plot is basically our histogram of the error. So what I have done is I have taken this error. So ERR is y minus y hat, and then I have used this np.histogram to actually get the count and the bins. Okay. And then I am showing using this plt.hist. PLT is the matplotlib. Using this, I am showing the histogram here. So you can see that the maximum is 0 error, but then there are all these other errors. Okay. So there is 1, 2, 3, 4, 5 till about 11 or something, that is error. Okay. And here I have also plotted the MAPI and the R2 score. Okay. So this is the output. Now the last thing is sort of somewhat instructive, at least, is that I have now plotted this regression model coefficients. Okay. So I have plotted these coefficient values. So so after bloating up, there were about 22, I think it was a 22-dimensional model. Okay. And I am now plotting how the W is looking for each of these guys. Okay. So for cylinders, for this thing. So you see most of the W's are looking high or low for this model year categorical variable. Okay. So basically, this is like a problem, right? And this is doing kind of a overfit. Okay. And so how to check that? Okay. Okay, so here I have done another thing where I have basically not without the dummy variable. So I have not used the dummy variable and done the same thing, okay, what I just described earlier. So again, the same thing, you see this is the scatter plot of the predicted variable and it is over predicting, and there are some errors. Actually, there are slightly more errors, but the MAPI is also slightly more. So by doing the by the categorical to binary, we were able to do a little bit better fit. Okay, now we are doing a little bit worse fit, but not much difference. The previous one was also pretty bad. Okay, and again you see here it is kind of assigning a lot of weightage to cylinders. So here it is very clear, cylinders, modeliers, origin, it's assigning a lot of weightage to this. Okay, even though, I mean, if you try to think, it is trying to predict the miles per gallon. Okay, that should not depend on I mean, it may depend on cylinders, but definitely it should not depend on modelier or origin. Okay, so it should not be so much. Okay. Okay, so yeah, okay. Now let us see. Let us try to do the ridge regression here. Okay, so by the way, ridge regression is just another name for L2 regularized L2 regularized least square regression. Okay, so so yeah, it's from linear model. You just have to import this ridge function. You can see it is very similar to that. Yeah. One extra parameter here you have to add, which is this alpha parameter, which is basically how much weightage you are giving to the so this is like the lambda parameter. Okay, how much weightage you are giving to the yeah, you can see this here. So alpha times norm of w square plus the error is anyway here. Okay, so this is what it is computing. Okay. Okay, so now what you can see is that okay, so let us go to the scatter plot. Yeah, it is still bad, it is not very good. Yeah, it is still pretty bad and it's giving. So let us try to increase the alpha and see if that can help a little bit. Okay, before going to increase the alpha, let me try the other thing that I just told you, which is that you should not actually look at just the training set error. Up till now we were only looking at the training set error for the real data part. Okay, so what I do, I now use this test train test split here. Okay, you can see that I'm doing this train test split, and basically I am saying here that 20. So you can see the again the so documentation for here. Basically you need to give the arrays. So the arrays is like the input x and y array. Okay, so yeah, and then it will give you x train x test and y train y test, and you have to also say what fraction of it should be going to the going to the test set. Okay, so that is the test size. So I'm saying 20% data should go to the test set. Okay, here. Okay, and I'm doing a random sampling, so you can see, you can specify many other things. One of the, so shuffle is by default specified to be true, so that is fine. You can also do a stratify. So what stratify does is it stratifies the sampling based on the y variable. Okay, so basically it will, so if you have like a class imbalance, it may be useful to have stratify as true or something like that. Okay. Okay, so anyway, so let us try to do this here. Okay, so I have done this. Now let me just run everything again. Okay. Okay, so yeah, so it's spewing out a bunch of things. So first it is spewing out the training error, and training error is like that. So about MAPI is about 11 and R2 score is about 0.83, and this is the training error histogram. Now here the test error, okay, yeah, so the test error is much higher, but somehow the histogram is I don't know why it is coming out wrong here. Yeah. Yeah. Okay. But you can see that the test error is somewhat higher here. Okay. So it's doing a bit of overfitting, and then you have the coefficients here. Okay. So let me. But here I was doing like the reg model, right? So I was doing. Yeah. So let me try come back here and try to fit with a higher value of alpha. Let us see what that gives us. Okay, it is still doing a kind of a bad fit. Let me just. Okay, so are we? Okay. Okay. So yeah. Here is the regression with this thing. Okay, so let me run this with. Yeah. So you see, I'm running. So I just want to see show the effect that alpha has on the training and test performance. So if I run it with alpha is equal to 1, okay, you see, I'm getting, okay, I'm getting a SMAPI of 11.7, and here it is close to 11. Okay, SMAPI of 11 and 0.8 and 0.86. So this is slightly better. Okay, so in this particular case, test set performance has become slightly better. Okay, let me run it once more. Yeah, so you see the test set performance has become slightly worse here. Okay, yeah, so this is the normal thing, right? So test set performance is slightly worse, and yeah, training set performance is slightly better. Now I try to increase the alpha. So let me increase it to 10 now. Okay, you see test set performance has become more comparable, in fact slightly better than the training set. So let me do it once more. Okay, yeah, slightly worse, yeah, slightly worse or very similar, okay, to the training set performance. So you see earlier with alpha, so let me also, so again you see very similar, in fact yeah, slightly worse in this case than training set performance. Yeah, here again slightly worse. I mean, so you have to run it many times to get some stable results, but compare this to something like, let's say 0.01. So if we do this as 0.01, what happens? Let me try to run again. Yeah, you see the test set performance is consistently now worse than this guy. Okay, at least SMAPI wise, the test set performance is consistently worse. Okay, here actually MAPI has become very large. So this is one problem with MAPI. You will see that, sorry, this is a different thing I'm running. Let me come back here and run. Okay, yeah, yeah, okay. So yeah, you see SMAPI wise at least, the performance is slightly worse all the time. Okay, so you will see if you run the experiment many times, you will see that if you increase alpha, your difference between your test set performance and training set performance will reduce. So reduce in the sense that your test set performance will be your test set error will be much closer to training set error as opposed to much higher than training set error. Okay, so this is one of the things I wanted to share. Yeah. Yeah, so in the interest of time, I will not go through the other data sets, but it is all there in the code, so you can just modify and run it. So are there any questions or comments? Okay, alpha is basically this lambda that I showed in the slides. It's the regularization parameter. So let me just go back here a little bit. So yeah. So yeah, this lambda is actually alpha. Okay. Okay, so we are done with regression, but we also had to do classification. So what do we do? Do we continue, or what are the?
So in the
Do we take 5 minute break and then continue, or?
in your next tutorial, next year. So in that there you have plans, or can it be accommodated in that?
It can be accommodated, but also there is some. So actually, we want to talk about a bit of deep learning there. So
then we can have continue.
How long?
no, whenever we can stop at any point in time and continue from there. Anyway, Professor Shaukat will also teach. So some of the things may be taught in the next class itself. So I just wanted to maybe half an hour we can continue. We can take a 5 minute break and then yeah. So is that fine, or?
No, we will take a 5 minute break. Then we will again continue today itself for another half.
So let's take a 5 minutes break. I mean, yeah. I mean, if it's not terribly inconvenient for you guys. Is
Right,
much better.
so we
Everything
will
I
be
can just
taking
do from my laptop and.
this is on.
Just give us a minute. We'll confirm that the YouTube is running. Then we'll start.
Okay. Okay. So welcome back. So I know, like, I will try to make this very brief, and I'll go a little bit fast. So if you have any questions, just ask. So I think most of you know what is a classification problem. Okay. So if you have a discrete label which you have to predict, that's a classification problem. So for example, if I give you a document, then the topic of the document is predicting topic of the document is a classification problem. So it could be sports, science, news, etc. Similarly, if I give you a medical image, whether it is anemic cell or a healthy cell, classifying that is a classification problem. Okay. Yeah. So I think we have seen many applications. So we will not get into it. So one of the differences between classification problem and regression problem is the way we evaluate the classification problem or the classifier. Okay. And a very common way, like I said, there are many metrics using which you evaluate a regression model. There are many metrics using which you can evaluate a classification problem. One of the metrics, or one of the most commonly used metrics, is the accuracy. Okay, so accuracy is basically the number of times we have classified a training data point correctly divided by the total number of test cases, or in this case the total number of training data points. Okay. And this step, we already know that you have certain training data, you use the learning algorithm to produce the model, and then you use test data to produce the accuracy. Okay. And you look at both the training set accuracy and the test set accuracy to actually try and take a decision. Okay. Now, the question is that can we do we need to, have separate, a separate way of training a classifier, or can we simply treat a classification problem as a regression problem? Okay. And so very commonly what is done, so the kind of classification problem that we will be looking at here is the binary classification problem, which means that there are only two classes. Okay. So for example, it could be anemic versus healthy. So this is a very common classification problem that many people try to solve. So we will be using, so we will be solving that. There is also the multi-class classification problem. We will not discuss it much today. Okay. But maybe later it will come up more. Okay. So now, if we try to, so first we try to do what is called this least squares classification. So we have already seen least square regression. Okay. And we try to do least square classification. So how do we do least square classification? We say that the two class labels, okay, In regression, there was this all these values, real values, which was the label t. Okay. In classification, it can only take values +1 or -1. We say this. Okay. So one of the classes is +1. Let's call that positive class, and the other class is -1. So t is only +1 or -1. Okay. That is going to be the predicted value. And we use the same objective, this ED objective that we are so very familiar with, which is the squared error objective. Okay. And then we can get this least square estimate. Okay. So the question is this good? Okay. And now here I am showing this least square classification. Okay. So what is this least square classification? So you have this let's say the red is the positive class, and let's say the blue is the negative class. Okay. And let's say this green is the true class boundary between the red class and the blue class. Okay. So that is how I have generated the data. Okay. And if this is the data, and if I use the least square classification, okay, my purple thing will be the classifier, because what am I doing? So I am trying to say that this red class should be on the positive side of the given classifier. If you see here, it is saying that x transpose w, which is y of x, okay, or w transpose x, whatever, okay, that should be +1 if t is +1, in which case if you predict -1, that should be 0, and vice versa, right? So it should be predicted +1 for the red guys and -1 for the blue guys, and that is happening more or less if you use this. I'm looking at the left plot here. So if you use this purple decision boundary. Okay. Now consider this right hand side scenario where you have the same data points, but you have some additional outlier blue data points here in the right hand side bottom. Okay. Now if you try to do this least square classification here, these blue data points also has to be predicted as -1, but these are very, very far away from these other blue data points. Okay. So it will try to predict both these blue data points at -1. Okay. So it will end up cutting off some of the blue data points. So some of the blue data points will actually go to the other side of this. This is the predicted decision boundary, which is this purple line. Okay. And this is the reason why we don't do a least square classification. Okay. So I hope this is clear. So the least square classification is not good. So what can we do to make it better? Okay. So basically this brings us to the problem of logistic regression. Okay. So what is logistic regression? So it is basically, you can think of it as we are still doing regression, but now instead of regressing on the actual predicted value, we are regressing on the log odds ratio. So what is happening here? So let me go here. Okay. So what we are saying is, in this case also it's a linear model. What do I mean by linear model? Basically, whatever are the input features, the decision boundary, okay, this is the decision boundary that I'm showing. The decision boundary is a linear function of the input features. In fact, the decision boundary is this linear w, w0 plus summation wi xi equal to 0 is the decision boundary. Okay. So whatever goes on the positive side, whatever goes on the positive side of this line is the positive class. Whatever goes on the negative side of this line is the negative class. Okay. So this is the decision boundary and this is the classification rule. Okay. So now what we are saying here is that moreover, you see we have this sigmoid function. The shape of the function is clear. This is called the logistic or the sigmoid function. Okay. It is 1 by 1 plus e to the power minus w transpose x. Okay, and this we postulate for the time being, we will see why, is the probability that the given training data point x belongs to the positive class. So that's what we have written here, that probability that y is equal to 1 given x, okay, is given by this sigmoid, and here is the curve. Okay, so if your z is greater than 0, you can see that your basically, so one thing you can see is that if your z or this w transpose x is equal to 0, it will be 1 by 1 plus e to the power minus z, which is 1 by 1 plus e to the power minus or plus 0 is same, which is half. Okay, so at the decision boundary, the probability of positive class and the negative class is exactly half. Okay, so this is good. Okay, and then on the positive side it grows to 1, and on the negative side it goes to 0. So this is the probability of y being equal to 1. Okay, so this is good. Okay, now what we were saying that the so if let's say probability of y equal to 1 is this sigmoid, then what is going to be the probability of y is equal to 0? This is nothing but, because there are only two options, either y is 0 or y is 1. I mean, by 0 can also be replaced with minus 1. Okay, so either y is 1 or y is minus 1. So the probability of y is 0 is 1 minus probability of y is 1. Okay, and that is this number. Okay, so it's basically e to the power z by 1 by e to the power z. Okay, so if we now take the odds ratio, which is the probability of y is equal to 0 given x by the probability of y is equal to 1 given x, this is called the odds ratio. This turns out to be the exponential of this linear function, which means that log odds ratio, this log of ratio of probability, is the linear function. So that is the key idea behind the logistic regression, that instead of trying to predict as a linear function the decision variable, which is y, you are actually predicting the ratio of probability of y is equal to 1 by probability of y is equal to 0, or in this case the other way around. It will just change the sign of the w. Okay, nothing much will change. The definition is doable both ways. Okay, okay, so this is clear. Okay, so this is the log odds ratio. Okay, so now just a little bit of maths, I will go over it very fast. Okay, so what you can do now, then, instead of writing probability of t is equal to 1 is something like that, we can directly write probability of y. If we just say that y is plus minus 1, we can simply write probability of t given x comma w is sigmoid of t times w transpose x. Okay, so w transpose x is the number, is the linear number, times t. So this is plus 1 or minus 1. So as you substitute t is equal to plus 1 or minus 1, you can just check that you will get the correct number here. Okay, so you have probability of t. Okay, now you go back to the same log likelihood thing. So given a training data set, you calculate the log likelihood, and then you basically do a maximum likelihood fit of w, which is just w star, which is argmax over w, this log likelihood. Okay, and then so this is the final problem, and you can write a minimization version of the same problem. Okay, this is just calculation. So finally you get this loss function EW, which is log of 1 plus e to the power minus Tn W transpose Xn. Now this is a very different loss function compared to the least square loss function that we have seen, but you can check, it is sort of a good thing that this also turns out to be a convex loss function, and you can use exactly the same mechanisms that you have used for the least square regression. Okay, and in fact, you can also use exactly similar mechanisms for regularized. Okay, so you can have regularized versions of this loss, which we have just written here, which is the L2 regularized version of this particular loss function. Okay, and this is how you estimate W. Okay, yeah, I am just listing the derivatives, nothing much. Okay, and then you can do gradient descent to actually calculate the best W. Okay. Okay, so this is about the logistic regression formulation. Okay, so just to summarize, the logistic regression gives us a probability of positive class and negative class also. Okay, as a linear function, and it also creates a linear decision boundary. Okay, okay, so this is about logistic regression. Now we go into what is arguably the, I mean, logistic regression is also very widely used classifier and very widely used actually, but probably SVM is slightly more commonly used. Okay, now what is the difference between these two? Okay, so so we saw the, you know, the least square regression does not work. Okay, so what happens when we try to fit logistic regression to this data? Okay, so this is the actual decision boundary. Okay, by the way, the prediction function for logistic regression as well as for support vector machines is exactly the same. Okay, the decision boundary is exactly the same. It is W transpose X plus B is equal to 0. Okay, if W transpose X plus B is, so we sometimes write the prediction function as sine of W transpose X plus B. Okay, for both prediction logistic regression and SVM. Okay, so so basically, if this W transpose X plus B is positive, go to the positive class, negative, go to the negative class. Okay, now you see all these variations of the classifier. So you are getting these variations of decisions boundary by changing W and B. Okay, so all these variations will give you a roughly same kind of logistic loss, because, you know, for all these variations, most of the training data points are on the correct side. Okay, and the, you know, so if you recall sigmoid loss, what does it depend on? It depends on the fact that your training data point should be on the correct side of the decision boundary, and it should not be too close to the decision boundary. If you recall, so let me just go back to this sigmoid function. So this is the sigmoid function, right? So you see, so long as it is slightly far away from sigmoid function, roughly your this P of y by P, you know, this log odds ratio is going to be roughly the same. Okay, so it's not going to be too different. Okay, so it's going to be roughly 1 basically, not 1 but whatever this, you know, P of 1 by, so P of y is equal to 1 by P of y is equal to 0, that value. Okay, so it's not going to be too different for all of these guys. Okay, so the question becomes then which one to choose, but visually you can see that one of them is better than the other. Okay, which one is better? Okay, so what SVM does is it formalizes this notion of which one to choose from many of these guys. Okay, and it formalizes that using this notion called the margin. So what is the margin? The margin is the distance. So first of all, it says that, let me consider, by the way, I mean, we are right now describing a toy situation where the data set can be actually nicely split into the positive class and the negative class using a linear boundary. Okay, so in this situation, okay, you take the closest positive point to the linear boundary and you take the closest negative point to the linear boundary, and then these need not be necessarily equidistant, but you can adjust it such that they are equidistant. So you can adjust the bias a little bit such that they're equidistant from each other. Okay, and in that case, the margin is actually the width of this particular red strip. Okay, which is separating these positive points from the negative points. Okay, so this one is a narrower margin than this one. Okay, and intuitively you can understand that this larger margin decision boundary is probably a better classifier. Okay, so this is the intuitive thing. Okay, and this intuition, so we will come to the support vectors in a minute. Okay, so this intuition is mathematically formalized in support vector machines. Okay, and how is it formalized? So what SVM does is, instead of having just one decision boundary, it talks about 3 different decision boundaries. Okay, so the first one is W transpose X is equal to 0, which is going to be the actual classifier boundary finally. Okay, but at the time of training, it talks about these margin boundaries, or whatever you want to call them. So there is this plus plane. So I have just called them plus plane and minus plane. It need not be called that. I mean, it's not standard terminology, but these are that W transpose X plus B is equal to 1 and W transpose X plus B is equal to minus 1. And now what it is saying is that for positive points, not only should it be on the correct side of W transpose X plus B is equal to 0, it should be actually on the positive side of W transpose X plus B is equal to 1 also. Okay, and similarly for the negative training data points. Okay, so this is the situation, and there should not be any data points in this margin region. Okay, between +1 and -1. Okay, and if you do all this calculation, so then what you are saying is you are now imposing constraints. So you are imposing constraints for one constraint for each training data point like this. Okay, and then if you use the convention that yi is +1 and -1, you can write it all into one constant. One constant meaning that one formula per training data point, which is this yi times W transpose xi plus b is greater than or equal to 1 for all training data points. Okay, and then you can also estimate the margin m, and it turns out to be this 2 by norm of w. Okay, so you can just do some basic coordinate geometry calculation to figure this out. Okay, the distance between two hyperplanes, because one is +1 and the other one is -1. Okay, so and then you have to divide by norm of w. Okay, so then you have your first formulation of maximum margin SVM, which is that you maximize the margin, which is 2 by norm of w, and then it is the same as minimizing norm of w squared by 2. Yeah, so nothing changes, and subject to these constraints. Okay, which we have already seen. Okay, now so if we do this, so now we have a constraint optimization problem. Okay, and this is also a convex optimization problem. Okay, so all these constraints are convex, and also the objective function is of course convex. Okay, and so you can basically try to use the Lagrangian duality. Okay, to solve this problem, and you can solve it exactly using the stationarity, primal feasibility, dual feasibility, and complementary stackness conditions. These are some mathematical results. I'm not going into details of it. I will just give a little bit of intuition here that the stationarity is basically saying that it should be a stationary point with respect to the optimization variable. Okay, then primal feasibility simply says that the constraint should be satisfied. Dual feasibility says that the that your basically your so just to give you an idea what the Lagrangian represents, it represents the penalized cost of the constraint violation. So it has the f of x, okay, which is the objective function, which is to be minimized. Okay, to it adds all these mu I times gxi, which are all supposed to be less than 0. Okay, so mu I times gxi is supposed to be less than 0 because mu I is supposed to be greater than or equal to 0 and gxi is supposed to be less than or equal to 0. Okay, so the moment some constraint is violated, what will happen is its mu I can be arbitrarily high. Okay, constraint being violated means what? Means gxi is not less than 0, so gxi is positive. Okay, and mu I for that is arbitrarily high, so that is going to push up the Lagrangian value very high. Okay, so this is one part. Okay, and the last part is what is called the complementary slackness, that the product of mu I times gxi should be equal to 0. So either gxi should be equal to 0, in which case it can have high mu I, okay, or mu I should be equal to 0 if gxi is actually less than 0. Okay, but the product should always be equal to 0, otherwise again your Lagrangian will not be equal to f of x, there will be some other value. Okay, so that is also not correct. Okay, so that was the intuition. There is a lot of mathematical theory behind it, which I am not getting into it. Okay, okay. So now this is basically the Lagrangian, and this is the loss function. So you can see that yeah. So you can see the Lagrangian function which you want to minimize. Okay, now I am just skipping some of these, some of these maths. I just want to mention that these alpha i's are the Lagrange multipliers which quantify the violation of the constraint. So the number of alpha I is equal to the number of training data points in the data set. Okay. So if you do all the calculations, so you have to mention the 4 conditions that I talked about. You have to maintain those conditions, which are the stationarity, the primal feasibility, the dual feasibility, and the complementary slackness conditions. Okay, and if you try to maintain these conditions, what you will see is so the first two the stationarity conditions give you that W is equal to summation over I is equal to 1 to n alpha I yi xi. Okay, this is just a mathematical thing, and summation over alpha I and yi is equal to be 0. And again, with a lot of substitution, okay, what you see is that your Lagrangian becomes only a function of alpha I and yi. You are able to eliminate both W. So you had, for any constant optimization, you have to optimize with respect to the primal variables and the Lagrange multipliers. Primal variables are W and B here. Lagrange multipliers are alpha I here. But what you are able to do through the stationarity is you are able to eliminate W and B. Okay, you can just go over the calculation at length, and you will be able to see that you will be able to eliminate it. And finally, your Lagrangian is only a function of the Lagrange multipliers, that is the alpha I value for each training data point I. Okay. So if this is the case, then so this is basically your now new objective function. So there are some more constraints here also. This is not completely unconstrained because your alpha i's have to be positive and alpha I has to be equal to 0, which we saw. But these are not very big constraints. Okay, so this is just one constraint, and alpha I positivity constraint is also not too much of a constraint. Okay, so you can solve this using quadratic programming or any other. So I'm not going into the algorithms for solving this. There are a whole lot. That's a whole bunch of literature on that. So I'm just keeping that. Okay. But one thing I want to mention here is that complementary slackness means that alpha I times 1 minus yi times w transpose xi plus b should be equal to 0. So for any training data point I, either it is lying on the +1 or the -1 plane, okay, in which case its alpha is going to be positive, non-zero, or else its alpha is going to be 0. Now, if its alpha is going to be 0, it does not matter what that data point is. If its alpha is going to be 0, its contribution to W is 0. Okay, whatever yi and whatever xt. See, you remember the formula for W. W is simply summation over I is equal to 1 to n alpha I yi xi. Okay, so for vectors for which alpha I are 0, these are useless from the point of view of calculating the model parameters. Okay, only vectors or only data points for which alpha I is positive, those are only going to be responsible, and those are the data points which are also lying on the boundary. Boundary means the yi times w transpose xi plus b is equal to +1 or -1, one of the two. Okay, not one of the two, depending on the yi basically. Okay, so which boundary it lies on. So these are also called the support vectors. Okay, so this is the picture basically. So here you can see this alpha is equal to 1.4 here for one class, and alpha is equal to 0.6 and 0.8 for the other class. So these are the support vectors. All the other points are meaningless. So these are the points that define this particular decision boundary W transpose X plus B is equal to 0. All the other points, you can just move those points around so long as they are not crossing over to the other side of the decision boundary. They will not define the decision boundary. Okay, only these 3 points, this point from the class 1 and these 2 points from the class 2 are all that is needed to define the decision boundary. Okay, and now this has a problem, so I am not getting into this problem too much, just that you may not, so it may be that your data set is such that you are not getting such a well defined margin. In that case, you have to allow for some slack, and this slack will basically be the error, and you can also minimize these errors, and this is the formulation for minimizing this error. And if you do again the same calculation, you come back to the the similar formulation, except that now alpha I has a upper bound of C. Okay, and this C is a parameter that is input to the SVM which you run. Okay, okay, so this is basically the soft margin support vector machine formulation which we solve. Okay, now okay, so okay, so let me just mention this one. So you see, sometimes because of outliers, this soft margin support vector machine is also more robust to outliers than the hard margin version, which we determined later, even for linearly separable data sets. Okay, okay, now there is the final thing that so all this was thinking about the linear decision boundary. Okay, but so there was one very important observation made. So let me just try to make this observation here. If you see the dual formulation, so this is the dual formulation. If you remember, this was the formulation of the SVM. Okay, you see X size or the training data point features appear only as a dot product in this particular place. Okay, and this dot product, if you take the linear decision boundary, then this will be just the dot product between xi and xj. Okay, but you can, so the space is here defined by the inner product itself. So whatever is the geometry, this geometry is designed by the inner product itself. Okay, so what you can do, you can use this kernel trick or this kernel function to actually design different geometries. Okay, so what do we mean by that, right? So so what you can do, you can say that this kernel function k xi xj is, instead of xi transpose xj, it is now this phi of xi transpose phi of xj, where phi is some feature map. We have looked at basis functions earlier, so this is somewhat similar to it, right? So whatever xi, and xi can be a vector also, you pass it through a feature map. Okay, so this is what we are showing here, that this is your input space. Okay, your input space has a nonlinear decision boundary, so you pass it through this feature map phi, so that hopefully in the feature space the decision boundary is linear. Okay, so this is basically what you are hoping for. Okay, and so what are the different feature maps you can do? Okay, so for example, you can do so the question may come that so for example, suppose I want to use for a d-dimensional data. Okay, let's say in this case just a 2-dimensional data. Okay, so our original data is 2-dimensional. I want to use a second order polynomial features, okay, or second order polynomial kernel. Okay, so if I were to try and write the actual feature map, it will look something like this. Okay, so there will be 1, there will be some terms with x, there will be some terms with x1, sometimes with x2, then there will be x1 square, x2 square, and x1, x2. Now this number of terms increases exponentially with the degree. Okay, that is the problem, that number of terms increases exponentially with the degree. So if you were to compute this phi of the feature map phi, and then compute the dot product as phi of x times phi of y, you have to take a dot product between two feature vectors which are exponential in size. Instead, what you can do this bottom calculation here, which is 1 plus x1 y1 plus x2 y2, which is the you can check that this does the same calculation, but it does only linear number of terms. Okay, so it does a dot product between in the original space, then adds a 1, and then raises it to the power 2, or it can raise it to the power 3, 4, whatever it is. Okay, similarly, I will not go into this Mercer condition and everything. Okay, what you can see is that this so there are some conditions for this to work. So this kernel matrix should be positive semi-definite. Okay, but essentially what I want to say here is, yeah. So what I'm going to say here is that there are many different kernels that you can use. Okay, so you can use the polynomial kernel, which I just described. Another very widely used kernel is this radial basis function kernel, which is, you see, kernel between x and y is norm of x minus y whole square by 2 sigma square e to the power minus of that. Okay, then there is hyperbolic tan kernel, which does not satisfy Mercer condition. So these two, polynomial kernel and radial basis function kernels, are very widely used. Okay, and then if you have some kernels, okay, you can also combine them in these manners to produce other kernels. Like you can do linear combination, you can do exponentiation, you can do product. All these things actually also create new kernels. Okay, so with this I will just stop. So essentially here is a way of creating different. So this is an actual data set where you are trying to fit different SVMs to this particular kernel. So the first one is using linear kernel. Okay, is getting a certain margin. The second one is using a polynomial kernel. Okay, is getting a slightly larger margin. Okay, and third one is also using a polynomial kernel, but it's using a polynomial kernel or degree 5. So it's able to create a slightly larger margin, as you can see. Okay, so that you can also I mean, take my word for it that the margin, the value of the margin, is also an indicator of how much you can generalize. Okay, you can see that just like in case of regularizer, the norm of the parameter was kind of an indicator of function complexity. Okay, or how much you are regularizing, and so basically that how how much robust is your learning. Here also it's the same case. So the larger the margin, the more robust is your machine learning method. Okay, and here is the nature of Gaussian kernel, and Gaussian kernel has sigma. Okay, so you can control the sigma to create see what kind of decision boundaries you can generate. Okay, so these are decision boundaries in the original feature space, and you can see that if sigma is high, it is looking like a polynomial kernel, but if sigma is low, then it creates very, it creates like circles. Okay, so it creates decision boundaries which are circles. So here you see these two circles are basically red class, but all the other space is just the blue class. Okay, so you can get very complex decision boundaries using the Gaussian RBF kernel. Okay. Okay, so any questions or comments, and maybe we will stop here. We will continue with cross validation and other things in the next class, or yeah, we'll see. So in the next class we will continue, or if Professor Chatterjee covers it in tomorrow's class, then we can just skip it, and then we can directly go to deep learning in the next class. Okay. Any questions or comments? So I did not show you the demo for the classification, but I think it will be relatively easy to code that up. I mean, you just have to change the classifier. The instead of reg model, you have to use a classifier model. Okay, so yeah, I can show you maybe in 5 minutes in some time next class.
So, sir, Ashwin Amrita Raj is asking for sharing the slides for further reference.
Yeah. So slides I have already shared. Yeah.
And there is one question from RK Goel. Won't be changing data after projecting them through kernels for any further inferencing. And if we require original data points back, I guess this is a comment.
Okay, so the question is, won't we be changing the data? Yes, we will be changing the data. So let me just show this. Okay, see. Okay, so let me just step back here. So the kernel. Okay, let me. Yeah. So we are. It's very similar to what we did in case of feature transformation, except that here we are doing an implicit feature transformation. Okay, so here you see this is the input space. Okay, now we only have a linear classifier, so we can only generate decision boundaries like this, but we can see the decision boundaries should be like this. So what do? We use this phi map to change. So the purpose of this phi map is to actually change the data. It changes the data such that a linear classifier fits the data very well. Okay. Now the question you will ask is, then sir, how will I know which feature map changes the data in the correct manner? And the answer to that is, you don't know. So you try out various kernels. So what are the kernels you try out? Again, you can try out the linear kernel, which doesn't change the data. In addition to the linear kernel, you can try out the polynomial kernel, or you can try out the Gaussian kernel, or even like I discussed here, you can try out a linear combination of polynomial kernel, Gaussian kernel, and so on and so forth. Okay, so all these are par for the course. Okay, so you can try out many different kernels. Okay, and you can see which one works best for your particular case. Okay, and there is also some literature actually on multiple kernel learning. So you can I mean, I can sort of point you to some which says that basically you can learn multiple different kernels along with so along with their coefficients. So right now here what I'm saying is that C1 and C2 coefficients are actually provided by the user. Okay, but there are methods which will learn this C1 C2 coefficients also automatically from the data. Okay, so so you can actually try out like combinations of different kernels. Okay, so I hope that that answers your question.
Thanks the instructor. And
Okay.
thank you, Dr. Shravansu, for such a nice overview of the data science techniques and a very useful, handful session. And thank you everyone for attending the session. If there is no further question, then we shall consider closing it. I hope to see you all tomorrow in the morning session.